Let's try to. So far, we had some Galois theory for finite extensions. Yeah. So, let me remind you what kind of Galois theory did we have? Our setting was the following. So we had a field, and we had a group. So it was a finite automorphism field automorphism group of field automorphism group of this K. Yeah, and we said that there is a correspondence between subgroups of G and bijective, yeah, one-to-one correspondence, subgroup of G and intermediate subfields, mediate subfields, well, intermediate fields in this extension, in extension of K over the fixed field, yeah. So such a correspondence. And so the question, what happens if we remove this condition? Yeah. So the question is what kind of groups. So you see that each, of course, we can to each subgroup here, we can associate the fixed field. Yeah. So okay. Yeah. The fixed field of H, and to each subfield, to each intermediate subfield, we can associate the subgroup here. So this the group of all elements of G that are identical on F. Yeah. So this is a subgroup, and this is yeah, and this is a subfield. Yeah. So in principle, we can do this way, proceed this way. Yeah. So, but the question is, what could we really have here? So, what I'm going to do is, first of all, to remark that this is not just a group. It's a topological group. So it is so G. So remark. So G is a topological, well, totally disconnected group. So this Hausdorff, of course, disconnected. Yeah, and so its topology. Well, if you know what is open compact topology, then this is exactly. So what is G? G is just a subgroup of the group of all permutations. Yeah, you can consider K just as a set. Yeah, so it's a group of permutations of this set. And on the, so you know that if you have two topological spaces, X and Y, then on the space of all continuous maps from X to Y, you have a compact open topology. Yeah? So in our case, K has discrete topology. So what is compact open topology in this case? This is simply, so base, we can say that the base, so a base of well, you see that we have to describe a base of open subsets, but actually we can describe a base of open subgroups. Yeah, and then we shift them. So a base of, well, let me write this explicitly. A base of opens, yeah, open subsets is the following. We just take so it is enumerated by finite subsets. So S is a finite subset, all finite runs over all finite subsets. And to each of these subsets, we associate the group of all permutations that are identical on S. So all G, all like in our group, such that the restriction to S is identical. Yeah, so it fixes those elements that fix each element of S. So pointwise stabilizer. Okay, and these are neighborhoods of the identity element, and then we shift them. So, well, we can write here G. So these are open base of open subgroups, and if we want a base of all opens, we just shift these open subgroups of opens. They are G. Just shift them by some. So for all G in our group, and for all finite subsets, finite S and K. Okay. Well, of course, if K is finite, then the topology is discrete, yeah, so it's not mere. Well, anyway, we allow this case.
Извините, а верно ли, что вот G умножить на вот эту сигма,
Yes.
которая, ну вот это
Yes, да?
S на месте, верно ли, что если умножить на это G, это будут такие перестановки, что оставляют множество GS на месте?
Нет. Это было бы сопряжение. То, что вы говорите, yeah, what you're saying is the following, it's a conjugate. So this is the subgroup. This is not a subgroup if G is not here. You see? It's a coset. I don't know, left or right or whatever. Don't know, is it left or right? So this K G of S. So what? You mean this one, yeah? So it's a subgroup, it's conjugate. Yeah, but these are cosets, so they are not, in general, they are not group. They are not group unless G is here already there, yeah? So just usual coset. Yeah? So a coset is a subgroup only if it is the same as the one when you put here 1. Yeah? Next, yeah, so this is the topology, and then the claim. The claim is that, so what do we have here? So what is written here? Here it's written the intersection over all elements S in F of these. Well, let's write this way in G, such that GS is equal to S. Yeah. So this is an open subgroup. Yeah. Little remark. One more remark. In any topological group, any open subgroup is closed. Any open subgroup is closed. Can you explain why? Yeah, that's right. Yeah, because so each subgroup H. Yeah, so if yes, so the complement G minus H is the union of all cosets. Yeah, GH, where G runs over G minus H. Yeah. So this is open. So this is open, and therefore its complement, that is H, is closed. Yeah. well, maybe I shouldn't put here disjoint union because here we have repeating cosets, yeah, so just union. Okay, and then yeah, so you see that this group is open and so it is closed, and we have an intersection of closed subgroup. So the conclusion that it is closed. So the conclusion is that any group that we can get this way is closed. So actually here we should put closed. Okay. And now it's okay. Now we can really state that this is angular correspondence, but instead of so this is one-to-one, but here we have to assume that we have to assume that this field extension is algebraic. Sorry. Oi. Sorry. We have to assume that this extension is algebraic. So we assume that it is a field automorphism group such that this extension is algebraic. Yeah, but well, you can ask how can we do this? How do we know this in advance? Yeah, so we take arbitrary group, and of course, if G is finite, then we know that this extension is algebraic. But can we say this in advance? If we are given some group, can we say immediately whether it is whether this extension is algebraic? Yeah. So and the answer is yes. So actually, the claim is that this extension is algebraic if and only if the group is precompact. So if G is precompact. Precompact means that it is you see that it is you can consider this group as a subgroup of group of all automorphisms of K or all permutations just of the set K. Yeah, and then precompact means that its closure in some bigger group like this, so that is its closure in all automorphisms or in just in all permutations is compact. And this compact means essentially this means profinite. So do you know what does mean profinite? No. Yeah. So let me remind you if you. So profinite. So what is a profinite set? So we'll just first of all, do you know what is inverse or projective limit? Yeah. Okay. Yeah. So we have a system of, for instance, a system of sets. We'll say alpha runs over certain. So a projective system. Well, say of sets, groups, or whatever. And then what does it mean, projective system? It means that this set is partially ordered. So I is a partially ordered set. And for any ordered pair, we should have a map from S beta to S alpha, so called alpha beta. And then the projective limit or inverse limit of this system is just the set of compatible collections. Yeah, so it is a subset in the direct product. So I assume that subset of direct product, and it consists of those collections. So a small s alpha, such that S alpha is in big S alpha, and these maps send each S beta to small s alpha for all ordered pairs. Okay. Yeah. So and now what is actually this so far this is just a set together with of course we have this is a set together with maps, just projection maps, as it is a subset in direct product, so we have projection maps onto each S alpha, and this set comes with a topology, namely we have a topology here, yeah. So it's you know, it's open sets are just so the base of open sets here are just take any so T is finite, J well, J is just a subset in I, which is finite, and we consider as a take a collection of S alpha in S alpha, where alpha is in this finite set. So base of opens. Well, maybe you already know what is Tikhonov topology. Yeah, so just знаете, да, все это? Знаете? Do you know this already? Maybe we can skip it, or let me.
Просто топология произведения.
Топология произведения, да. Yeah, just you simply consider the products of all but finitely many multiples, and this way you get, yeah. So the claim is that this is a compact topological space, and this is a closed subset of this topological set. That's it. Yeah. So. So Tikhonov's theorem states that the product of any collection of compact spaces is compact. So if in our case, if S alpha are finite, then inverse limit is compact. Is compact. В компакте. This is a compact. Yeah. So this is S alpha are compact because they are finite, and their product is compact as well. So, but actually, such sets called well, they're not just compact; they're profinite actually. Profinite. So profinite means inverse limits of finite sets. What? And profinite means implies compact, yeah? And totally disconnected because you see, because of Tikhonov topology is like this, yeah? There are no connected, yeah. Okay. Right. So. Yeah, so that's that was to say that compact. What does compact means? So in principle, how could we see that? Yeah, maybe another characterization of precompact. What does it mean precompact? G is precompact. It means that any open subgroup is a finite index. Any open subgroup is of finite index. Yeah?
Извините, можно вопрос? Вот сейчас было рассуждение, что если вот профайна, то компакт.
Да.
А вот на второй доске написано, что из компакт, ну, что тогда и только тогда.
Yeah, yeah. So you mean why compact implies profinite? You mean downstairs, yeah? If how to check that compactness implies profiniteness?
Ну, то есть это верно в принципе?
Нет, конечно нет. Конечно, no. This is not true in general because, for instance, you take.
Понимаю.
This is not profinite, of course. No. Or rather, well, we're talking about groups, so you rather take circle, yeah? Circle, it's compact, but it's not profinite, yeah? So, of course. But it means that here, when we deal with totally disconnected, you see that on the permutation, on any permutation group, we have a totally disconnected topology like this. Yes, you see that our topology comes from shifts of subgroups, and therefore it is totally disconnected. So totally disconnected plus compact implies profinite, because you take. Actually, this is exactly what is written here. Because you see that if you open, so if you have a compact space, compact group, and open subgroup, this open subgroup should be of finite index, yeah, because you take this decomposition to cosets, and you should have only finitely many cosets. Yeah, this precisely means that index is finite. Yeah. So this is. Yeah, so precompact or compact means exactly this. You see? So if so compact, maybe I should write here that a base of open. Base of open neighborhoods of the neutral element consists of subgroup. Consists of subgroups. Yeah. So if the base of open neighborhoods of the identity element consists of subgroups, then it should be then it is a finite index, and therefore our group is embedded into inverse limit of finite groups. Okay. All right. Yeah. So now it's okay. So we can pass to the. Well, actually, so the argument is, yeah, maybe. Yeah. So the argument, yeah, we should have yeah, we should, first of all, we have to check this bijection, and also we have to relate the algebraicity of this extension and profinite condition, yeah? So, well, this is more or less clear, because if, what does it mean that group is profinite, yeah? This means that that on each step we yeah, first maybe I should recall you some simple remark that any so if H is a subgroup of finite index, is a subgroup of finite index, then there exists another subgroup in H, which is also a finite index in G, and which is normal. H is normal in G, and this index is finite. Yeah. Well, you just you know the trick. Yeah. You just take name. You can take just intersection of all conjugates. Intersection of all. You can take say over. Take any representative in G minus H. Yeah? So it is, or you can say that this is the kernel of the natural action of G on the cosets. Yeah. So the group G acts on what? On what? On the cosets G by H. Yeah, just if you have G and G prime H, it is sent to G H, yeah, for all G prime. Okay. So this is a finite group. So its kernel has its kernel is finite, and its kernel is normal, and it is of finite index. What does this mean? This means that any profinite, when we deal with profinite group, we can actually present them as a limit of yeah, actually maybe maybe it's we can avoid this. Yeah, maybe we can avoid this because yeah, I mean when we deal with just arbitrary profinite group, then we can think of this as a limit of cosets. Yeah, but actually, maybe we should avoid. Sorry, maybe it's not, we don't really need this remark, because we can avoid this by yeah, so what I was going to say is that suppose that we have yeah, so what was the setting? Setting was if G was so now we are in our basic setting, this one. So K is a field, G is a field automorphism of K. is some field automorphism group of K. Yeah, so if G is profinite, or precompact, yeah, maybe just precompact, because we don't compact, then it has a base of normal open subgroups. Then it has a base of open subgroups consisting of normal subgroups consisting of normal subgroups. Yeah. You see? So just because of this, yeah. So we can always forget those subgroups that are not normal by replacing them by this intersection. Okay. So what does this mean? This means that it is dense in the limit of certain, let me call them G alpha. G alpha, so where G alpha are finite groups. Okay. Yeah, and dense means that well, it has essentially the same quotients, yeah, by open subgroups, yeah. So yeah, now yeah. So now what does this give to us? This gives us. Sorry, maybe it's not a good. Yeah, maybe we can. So let us denote by H alpha the kernel of the projection G to G alpha, and then so. So what is going on? Actually we would deal with a certain tower. So we have the subfield fixed by H alpha and the smallest field here fixed by the whole group G, and here the group is G alpha. Yeah. So. Well, and then, okay. Yeah, so now we just have to check that that all this, so we can start with the subgroup, go to the fixed subfield, and come back to this subgroup. Yeah, so. How could we check that this composition is identical? So this maybe I don't really need this.
Можно вопрос по предыдущему? Вот тут написано, что G чистый компас, если вот она, если ее замыкание in, ну, в автоморфизмах K или вот во всех перестановках из компас, а вот это OR, оно здесь потому что автоматизм.
Ну, это в смысле, что это не важно. It doesn't really matter where you take, because this is a closed subgroup here.
Ну, это был вопрос. То есть
It is closed in, because you see that what does it mean that let us try to prove this, that this is closed here. What is the group of automorphisms, field automorphisms? These are so what automorphisms of K as a field. Here's a field. What is this? This is an intersection over all pairs A and B and K of those elements, of those permutations such that G of A times G of B is equal to G of AB, and also intersected with those G of A plus B equals G of A plus G of B. So you see, for each so you see that we fix some pair, and we want to this pair to be sent to well, maybe it's easier. Maybe it's easier. Yeah, so essentially we want, what does it mean that this is a field automorphism? It means that yeah, and maybe it should not be zero, yeah, because everything can be sent to zero, yeah. So G, well, of course we can put here. Of course, we should fix something like 1, yeah. Yeah, and after that it is enough, yeah. So if it's not, yeah, so we just have to check that these subsets are closed, and why are they closed? Yeah, actually they are open, I think, yeah. They are open, they are shifts of and yeah, because doesn't matter, yeah, you see there is no matter which one we consider, which operation, yeah, so it's more or less the same. So it is the union of what? Of we can say that this is so over lambda mu in what, in K of those G in K1 such that G of A is lambda, G of B is mu, and G of A plus B is lambda plus mu. Okay? And this is open, yeah, because this is just a shift of those well, of course, there are not that many possibilities. For instance, it may be empty. Yes, it may be empty. Well, maybe there are two options. Either this is empty, or, for instance, A and B are the same, but lambda and mu are distinct. Yeah, for instance, in this case, it will be empty. But if it is not empty, then it is a coset of the group. It is a coset. So either empty, or it is a coset of the following group. K 1 A B A plus B. Okay. So you see that when we fix values of G on A, B, and A plus B, then it is precisely this coset. Yeah, and this group is open. Yeah, this group is open, and so this. Well, no, it doesn't work because we want this to be closed. Подстановка точки, в смысле? Подстановка точки, безусловно, непрерывна, да. В смысле, вы имеете в виду, что это будет... Сейчас, это будет что? Вы хотите сказать, что это будет какое-то ядро, да? Ядро, да. Yeah, you're right. We consider... Стоп. Значит, это мне не нравится, потому что ядра мне не нравятся, потому что эта группа простая. This group is topologically simple if this set is infinite. By the way, usual symmetric group, is it simple? Yeah, there are even permutations, you see. And also, if we deal with infinite, you see that when we deal with infinite sets, then it has we have there is a normal subgroup consisting of those permutations that fix everything but finitely many elements. So there is a finite subset. Okay, finite such that this element is identical on the complement to this finite set. So this is a subgroup. Can you see this? So we consider those elements that fix everything but finitely many elements. And it is a subgroup, yeah, because if we compose, so we have everything is fixed except finitely many, And then we have another element which fix everything but finitely many elements, and so they permute only those permuted by at least one of them, yeah? So this is a subgroup, and I claim that this subgroup is normal. So it is actually a normal subgroup. And of course, and here you again have a normal subgroup, namely even permutations. So here you do have even permutations, well, finite permutations. And this group is simple, yeah, because finite groups are simple. But the point is that actually, so you say that you may say that this is not simple, yeah, but actually the point is that this group is dense. So when I say that it is topologically simple, this means that there are no closed normal subgroup except the trivial one and itself. So that's why I don't like the idea of homomorphisms. Or maybe you mean something else. Yeah, so okay, so you say that this is a preimage of just preimage of some point. Okay, yeah, maybe, yeah, that's okay. That's maybe that may work. That may work. Yeah. So yeah, you're right. You're right. Yes, you're right. Yeah, it's okay. Yeah, that's good. Yeah. So yeah, so this is a preimage. So preimage of 0. So this is you see that 0 is a closed subset in K, and we consider map from this group to K. To K given by this difference, yeah. So G maps to, yeah. So Mikhail is completely right that this is good. Yeah. G A minus G of B. Yeah. So the claim that this is continuous. Yes, this is continuous, of course, by. Yeah, this is continuous, and its preimage is closed. Yeah, so that's yeah, that's the proof. Okay. So why the question is why is this? So it's closed. All right. Yeah, and maybe one more remark that here closed actually means closed means compact, yeah, compact, and also. Okay. And also, yeah, maybe one more remark that we may instead of closed subgroup, we may consider open subgroups. And the question is, can you say what will happen? So so you see that if we consider only open subgroups, then we get certain, not all intermediate subfields, but only certain ones. Which ones? Yeah, that's right. Yeah, so just those that that are finite over the, k over the smallest field here, k of j. Yeah. So now, okay, let's try to see what is going on when we start with certain intermediate subfields. So, for instance, f is between k and the fixed field of G. Yeah, so we, of course, we can just start with some. You see that any field is just a union or compositum of a certain finite fields. Yeah, so finite field extensions. Yeah, so we assume that f alpha is finite over kg. Yeah. So next we can let's restrict ourselves to just to finite ones. Yeah. So it's more or less enough. Yeah. Well, maybe we should look what does these correspondences do with certain. For instance, what happens if we consider compositum? Yeah. So let's try to see what happens with compositum. So compositum. So for instance, f prime goes to what? To so if we have two subfields here, then our automorphisms should fix both of them. Yeah. So this means that the compositum goes to the intersection. So GF intersected with GF prime. Let's denote this by GF. Okay, so compositum goes to intersection, and therefore, okay, and vice versa. If we have what happens if we have a subgroup here? Yeah, maybe. Maybe it's not very. You see that if we generate a subgroup by two subgroups, then it goes to again to the intersection. Yeah, so it should be KH intersected with KH prime. Yeah. So it is a subgroup in G generated by these two subgroups. Okay. Yeah. So for instance, here we just may try to start with finite extensions. So assume that that this extension is finite f over k. What happens then? Then we can consider the compositum of all conjugates. So compositum of all g of all g of f. And you see, this will also be so this is a finite Galois extension. Extension of AG. Yeah. Why? So why is it finite? Why is it Galois? Maybe compositum for all G in G. Is that what is evident, what is not? Well, you see, if f is finite over k, yeah, this means that it is generated by finitely many elements, yeah. So suppose it is doesn't matter, we can assume that it's generated by a single element, yeah. So then g of f is generated by an element in the orbit of this generator, yeah? And the orbit is finite, yeah, because it's an algebraic extension. We assume that our extension is algebraic, yeah? So there are only finitely many, all orbits are finite. And this means that this all G orbits in K are finite. Yeah, and that's why it is a finite Galois extension, a finite extension. Next question, why is it a Galois extension? So what does it mean that it is a Galois extension? It means that there is certain subgroup of automorphisms of f tilde, or C G prime, which coincides with the fixed field of K. So can you say what could be G prime? What is G prime? So well, just no, yeah, well, almost, yeah. You see, that's almost correct. And but G is the automorphism group of K. Yeah, but in a sense you're right that G prime is not well, it's not G, it is the image of G. It is the quotient of G by G quotient by GK. Yeah, GK. Sorry, G F tilde. F tilde. Yeah. So G preserves. Of course, G preserves F tilde, and it has a subgroup acting identically. So this is the group acting identically on F tilde, and of course. This is, yeah, so it's a Galois extension. It's a finite Galois extension, and so we have a finite, so we are reduced the usual finite Galois correspondence. Okay, and well, and essentially we can just Yeah, so thus we get correspondence between finite extensions and open subgroups. Yeah, open subgroups. Yeah, maybe. Yeah, and to get the full correspondence, well, you just you can look at open subgroups, yeah, for arbitrary open subgroups, and then reduce this to finite extensions. Yeah, just you know, essentially you just intersect your So yeah, maybe I should write this. So any H is what is this? Yeah, you can present H as a dense subgroup in the limit of its quotient by open subgroups. So open, well, even normal or open subgroups. Yeah, and this way you reduce to finite extensions. Yeah. Yeah, and maybe yeah, maybe just to mention one more Galois correspondence, that here it may be modified. Well, it is. It looks like a slight generalization of this correspondence, but essentially this is the same, but looks slightly more general. So here you see that here we assume that our extension is that this group is precompact and or equivalently that our extension is algebraic, but now we can do the following thing. We can simply sorry, it's not correct, not compact but precompact. Excuse me. Sorry. You see, the point is that no, it's not correct. It's not. They are not compact because we don't assume that our group G is compact. Yeah. So if we consider the whole group of automorphisms of this extension, then this would be correct. But otherwise, if we consider arbitrary group like this, then it's not correct. So it's closed. It's closed. So this implies that they are precompact. But of course, you can consider a smaller subgroup, which is also dense in the same group, and so well, just closed. Okay. Yeah, just closed. Now, so one more Galois correspondence, like which is essentially equivalent. So again, so K is a field. G. Well, maybe this will be an exercise, yeah, just to check that you are now familiar enough with this stuff. Yeah, so just any group automorphism, any field automorphism of K, any field automorphism group. Group of K, and then we consider we consider all closed precompact subgroups. Precompact subgroups of G. And on the other hand, we have those intermediate subfields. Fields in this extension as before. Let's call them F, such that F over Kg is algebraic. Yeah. Well, and the maps are as before. To each subgroup you associate the fixed subfield, and to each subfield you associate the subgroup of those automorphisms that are identical in the subfield. Yeah, so this is an exercise. Yeah? Okay. Okay. Yeah. All right. Then as in algebra 3, we pass to representations. Yeah. Yeah. So let me recall you. Well, of course, just to remind you that, Schur's lemma, yeah? Well, of course, you know the Schur's lemma. It's if we assume that M is a simple object of an abelian category, and then, of course, its endomorphism ring is a division ring. SQ field, yeah. And if for instance, if A is an algebra over algebraically closed field, K, and M is a simple A module, so it's particular case, but there will be some finiteness condition here. A simple A module, well, say left A module, which is finite dimensional over K. Then this endomorphism ring is just K. then endomorphism of M is K. Okay. Well, this is an exercise, yeah, or maybe you have already done this exercise at least once, yeah? Have you done this? Yeah? Okay, then, well, just you see that it is simple, yeah? So any endomorphism, what is the kernel of we take an endomorphism of this object. Its kernel is a sub-object. So the object is simple, so the kernel can be either 0 or everything, the whole M. Yeah. If it is 0, then okay, then it's just injective. Or it is if everything, then it is 0. It's even better. That 0 is 0. Yeah. Then if it is injective, then what is its image? Again, its image is either everything or 0. But it is not 0 because it is injective. Yeah. So it is everything. It is everything means that it is invertible. That's it. Yeah. So that's exactly. So everything is invertible except 0. Next, if in this particular case, when A is when we deal with a category of modules over an algebra over an sorry. It's an algebra. It's an algebra over an algebraically closed field K. Sorry, excuse me. Yeah. Well, because if A is a field, then any simple A model is K. Yeah, so it's not very interesting. Yeah. So yeah, in this case. So now, if again, so this is we know that M is so this endomorphism ring is a skew field, yeah. But it's as M is finite dimensional over K, this skew field should be finite dimensional over K, yeah. And well, and any finite dimensional algebra. Any finite dimensional division ring over an algebraically closed field is this field itself. Yeah. Well, this is an exercise. Yeah. So if you have never done this, check this yourself. It's a good exercise. So next.
Isn't it
Sure.
second race is just Jacobson intensity? It seems like
not really, because where do you use this condition? Yeah, because if without this condition, this is not true. No, it's like existence of eigenvectors. Yes, it's well, you have to really use this condition that the field is algebraically closed. Yeah. So yeah. Now let us pass. Yeah. So now we pass to some kind of representation theory. So it's or slightly more generally, we will deal with semi-simple rings. They are very simple, but well, they're semi-simple. I'm sorry, semi-simple rings. So definition is the following. An associative ring, ring. Well, we assume that that it is yeah. Yeah, maybe we assume that everything is with unit. Yeah. Is semi-simple. It's semi-simple. If it is not zero, of course, and it is semi-simple as a left module of itself. If it is semi-simple. Oh, by the way, do you remember what does semi-simple means? Semi-simple as a left A module. Yeah. Should I recall you? Semi-simple means помните, да? Yeah, so it's indirect sum of simples, or there are some other versions. Yeah. Yeah. Well, of course, you can say that this is the same as that any left A module is semi-simple. Yes. Semi-simple. Okay. And now let us, well, you probably know this Artin-Wedderburn theorem, which describes, so actually there are not that many semi-simple rings, but what is important that some rings that are semi-simple for certain quite obvious reasons, that they have some explicit description. Yeah, so it is Artin-Wedderburn theorem. So a ring, say, let's call it A. Is semi-simple. If a non-leaf, it is isomorphic. To the following finite direct product of matrix algebras. So NR, dr. Well, for some integers n1 and so on, NR, and division rings D1 and so on, dr. Yeah, and these integers for some, well, maybe I should write uniquely determined, uniquely determined. Well, of course, up to permutation, yeah, of these multiples of these factors. Okay. All right. So, first of all, let's decompose A as well, it is semi-simple, so it is isomorphic to direct sum of certain simple. So maybe I should write this, that this is an isomorphism as left A modules. Where UI are simple left A modules. Now we should look at this on the at the left-hand side. Yeah, here we have a unit. Yeah, so we really use that our Rinza with unit, and you see that this unit under this isomorphism goes to certain element here, yeah, but any element here lives actually in so it goes to something. Any element here lives in a finite direct sum, yeah. And therefore, as an A module, A is generated by this element. Yeah, so this means that this sum is finite. So this I sum is finite. And in particular, A is left Artinian. Yeah, so because just a finite direct sum of simple, well, it is, of course, it is Noetherian, Artinian, and so on. But so far we only need that it is Artinian. Now let's rearrange this sum. So we can say that A is isomorphic to, so here we had just direct sum simple modules, but now we rearrange this in this way. We assume that it is isomorphic to direct sum from 1 to R of HI to certain, yeah. Maybe I should say this way, that we consider just direct sum of M, yeah, N I, yeah, this way. In this way, yeah. So what is the difference? The difference is that we assume that these summands are non-isomorphic. Yeah, so this Li is not isomorphic to Lj for all distinct indices I and j. Yeah, and of course Ni is some integer, some positive integer. Yeah. Now, yeah, that's it. I think. Yeah, that's it. Now, what can we say? We can say that this is A is, of course, it is a faithful faithful A module over itself, yeah, because there is one here. And also it is semi-simple, so we can apply Jacobson density or by commutant theorem. So let's set di. So di will be just endomorphism ring of Li. So this is of course well, this is they are simple, yeah. So I'm sorry. Li. So Li are simple, yeah. So here, so these are Li just another name for UI. So we just rearrange them. Yeah, so this is more or less the same decomposition, but rearranged this way. So this is a skew field. And yeah, by Schur's lemma, yeah, if you wish. And that's it. So now we have Jacobson density theorem. So yeah, maybe we should write that what are endomorphisms. What is endomorphism of A? Endomorphism A as an A module. Of course, each summand is preserved by any. These summands are preserved, yeah, because different summands have nothing in common, yeah. So, and they are simple. So this will be just the product of all these indices of endomorphisms. Of what? Of Li to the Ni, and this is just you see that this is just the matrix algebra. Maybe well, I'm sorry, I didn't write that these are matrix algebras, and R size and R. Okay. Yeah, and so here we get these matrices over endomorphisms of Li, and that's it. Yeah. So now yeah. So. Okay, and so these are endomorphisms of. Oh, actually, we don't even need. Wait. Is that correct or not really? Yeah, actually, I think. Well, I'm sorry. I have another proof, here. So I'm a bit lost between two proofs. Yeah. So yeah. So I think it's enough because yeah, it's enough because you see that. Or you can say that something wrong here. Yeah. Is that correct so far? Yeah. So you see that actually what is always true, that endomorphism of any ring, endomorphisms of any ring considered as a left module of itself is the ring itself, but the opposite one. Yeah. So because how do you these these are, so you have to each element here, A, you have to associate certain endomorphism of A as a left A module. So you send X to X times A. Yeah, so this is true for, you don't really need some specific knowledge of this ring. This is true in general. Yeah. So yeah, it's strange. Yeah, so either something, because here I have a more complicated proof. Yes, so maybe, are you sure it's okay? Yeah. Yeah, it seems that it's okay. Yes, so we have here we have an isomorphism with the opposite. Yeah, so this way we get an isomorphism. Yeah, okay. So, all right. What else? Yeah, and now now should we have a break or?
Yes, it's time.
Hmm?
It's time.
Okay, all right.
Но в эту сторону доказали, они сказали, что обратно очевидно.
Что именно?
Вот это утверждение у нас.
Maybe you're right. Yes. We sorry. We yes. Sasha is right. We have only proven that if is simple, then it is isomorphic to this product of matrix algebras. But then yes, you're right. We have to check that if that this matrix that the matrix algebras are semi-simple. Yes, you're right. But well, actually, but this is. Let's finish with this because it's a trivial remark. Because it's you see that it is you can, instead of product, we can put here direct sum, and then you see that our algebra becomes direct sum of matrix algebras. Yeah. And the matrix algebras, so these ones, and the matrix algebra is isomorphic to direct sum of copies of d, I, and I. So these are columns. Yeah, you know, matrix algebra is split as direct sum of copies of column modules. Yeah, and this is of course simple. Yeah, I. So these are simple modules, and therefore it's equivalent. Okay. All right. Сколько там? 5 минут? 10? 5-10. А? Что? Кто шумит?
Ну вот я так делаю.
Это да. Нет, я имею в виду перерыв. Сколько?
А это, ну я не знаю, 10 минут.
10 минут, хорошо. Yeah, so 10 minutes break. Стоп. Это надо оставить. никакой элемент, понимаете, это что значит точно? Это значит, что никакой элемент в миллионе действует, кроме нуля. На единицу ноль получает.
У нас модуль единицы.
У нас не модуль, у нас кольцо.
Кольцо. Конечно. Просто там. Все.
Да, с единицы, да. Давайте берем скобочки, чтобы двусмысленности. Что это было? Вот, ну, вроде без обмана, да, там? Ну ладно, давайте тогда начнем, просто там все равно это, наверное, и так все знают, там теорема Машки, там все такое прочее. Это, да. Давайте просто вспомним, что это такое. Что-то вдруг. Или все помнят. Ну ладно, давайте. Так. Yeah, so we already have this description of semi-simple rings, but now we are going to have to present an example. Namely, we assume that G is a group, K is a field, then we consider the group algebra, then the group algebra, so KFG, so you see that this is simply, you know what's this? This is just the set, this is the set of finite formal sums, AI, GI, where AI run over field K, GI run over G. So this is just the set, and as well, this is actually a vector space over K. You can multiply these coefficients, and over K.
Over K.
Yeah. Yes. This G forms the group G forms a basis. Yeah. Yeah. So this is, and then well, the group, the group algebra. The group algebra. So algebra means that we have a multiplication. So this means that G A times A G times B H is just, you can imagine what's this. This is A B times G H. This is, and it is, well, you can put here sums, sum I, J, here also sum over J, is it in here sum over I and J, sum I, J. Yeah, so that's the group algebra, and then the claim is that it is semi-simple. So then G is semi-simple, if and only if G is finite. G is finite, and the characteristic of K does not divide the order of G. Does not divide by the order of G. Yeah? Well, this is just usual Mashke. Yeah, so it's Mashke. Mashke theorem. Well, the proof is quite evident. So if so, what should we do? We have so first suppose that the characteristic that G is finite. G is finite, and characteristic does not divide G. Then we have to show that this algebra is semi-simple. So you see that we have so it's this way, yeah, this way from. So assuming that G is finite, and we have to you see that semi-simplicity can be understood as that any submodule is a direct summand. Yeah. So suppose that M is a submodule of yeah, so just, well, or any, yeah, well, just any, yes, any. So suppose that N and M just are modules over this algebra, and we have to show that N is a direct summand of M. Okay. Well, the proof is quite straightforward. Namely, we have to prove that N is a direct summand. Yeah. So we simply fix any K linear map. Fix a K linear map from M to N, which is identical on N. Let's call it pi prime, and then we simply take an average of this pi over our group. So define pi of n as 1 over. You see that our order is invertible in the field, so we can simply or maybe U we take sum over all elements of G, or we assume that group is finite, of G pi prime G inverse of U. Okay. And you see that this is well defined. It is identical. So then it is identical on N. Yeah, because when you see that N is G invariant. Yeah, because this is a submodule. So when we apply G inverse, we stay in our N. Yeah, so N and pi prime is identical on N. So what we get is just G applied to G inverse and to U. Yeah, so that's identical on N. And well, and actually it is equivalent. Yeah, so we have to check that it is. Well, it's more or less clear. You just. What happens if you replace So, and so for any psi in G, what happens if we replace u by psi u? This will be 1 over G. Well, of course, it's clear that everything remains the same. So G, G pi prime G psi inverse G inverse u. Okay, and let's write this G as a composition of psi and psi inverse G. Yeah, and so you see that we can place xi outside of this sum, and inside we just get the same pi, as here as we wanted. Yeah, so this will be pi here. Yeah, so it is exactly what we want. Now conversely, so assume that our group algebra is semi-simple. Then we can look at what is called augmentation. So which sends some gi and sends to the sum of coefficients. So assuming that our algebra is semi-simple, there should be a map in the opposite direction. Yeah, but you see that here we have take any non-zero element. It should go to an element fixed by the whole group. Yeah, because here the group action is trivial. Yeah, so it goes to something which is fixed by the whole group. But you see that if something is fixed by the group, then this linear combination should contain all elements of the group. Yeah. So this is only possible only if G is finite. Okay. So otherwise, if G is infinite, then this is 0. Nice. Okay, and that's not all. So it is finite, and it goes to something, so actually, yeah. So one goes to what? To actually to the sum over orbit. It will be some coefficient times all elements of the group. G. But then coming back, let's call this epsilon. So then this goes to the A times the order of the group. So if the order of the group is divisible by the characteristic, that this is 0 and not 1. So this is 1 only if characteristic does not divide the order of the group. Yeah, and that's it. Yes. So this is usual Mashke lemma, and corollary. Corollary is that it's consequence for the representations of a finite group. So under the same assumption, so let G be a finite group. finite group. K be a field of characteristic not divided in the order of the group. Then and then there exists a finite collection of skew fields and numbers and 1 and so on and R, some positive integers, such that the group ring is isomorphic to the product of matrix algebras over this division skew fields. Yeah, and so these matrix algebras are just all possible representations of this group G over K. Yeah, so this okay. So this is more or less that's it about semi-simple. So you see the semi-simple are just matrix algebras and their products, finite direct products. But what we are going to do next is to generalize a little bit our setting. So we will deal not with semi-simple, not necessarily with semi-simple rings, but with some more general. And yeah, maybe one more remark that you see that all these in our definition we said that our rings are supposed to be semi-simple as left A modules, left models over themselves, yeah. But as you can see that there is no difference, yeah. So they are also semi-simple as right, yeah, because there is no difference between matrices over skew fields, yeah. So let's yeah, so we need a couple of definitions. So first of all, we need to define the circle. So the circle of an object of an abelian category this is just the sum or coproduct of all its simple subobjects. Is well, maybe I should write coproduct. Coproduct. Well, you can think of sum. Coproduct of all its simple subobjects. Objects. Well, actually, this is the same as the maximal semi-simple subobject. Maximal semi-simple subobject. Okay. Next, we need the radical. Yeah, let's call it M. The radical is the product. product in the sense that the intersection of all its maximal proper subobjects. Its maximal maximal subobjects. No, well, maximal means maximal proper, of course. Yeah. And well, of course, so empty. So, for instance, if there are no empty coproduct is just zero object, empty coproduct is the zero object. And empty product is just the whole, the object itself. Empty product is the object itself. Yeah, so in the sense that we don't intersect anything, so consider the whole object. Okay, so this is the radical of M, and also we need a particular case of the radical. It's namely, well, the Jacobson radical of a ring A, Jacobson radical of let's call it a J of A, of a ring A. It is the radical of A as a left modulo of itself. As ring A is the radical of A as a modulo of itself, as a left A modulo. Okay. Yeah. Now we have to do some exercise. Yeah, maybe just to make it clear the role of radical. So, for instance, what is the Jacobson radical of a semisimple ring? Почему? Yeah, so...
Можем дать все примерно сам.
Yeah, so it's yeah, that's right. So if we deal with something, maybe we should write here just semi-simple. Yeah, maybe if M is, we should write M. If M is semi-simple, if M is semi-simple, then the radical of M is 0. Yeah, because yeah, exactly. It is a direct sum of something, yeah. So of something. So yeah. So it is direct sum of mi's, where mi's are simple. And then the maximal, at least some of maximal objects are enumerated by so direct sum where we fix for each j we have say nj, yeah, nj will be the sum of all savants except jth, and then of course so we define for each j we define this this n and this nj is maximal and the intersection is 0, yeah. So it's clear, but now we want to consider the following properties. So we consider as before a ring A with 1, of course, and the claim is that so now we have to check that the following conditions are the same. The following subsets, the following or maybe a submodule. We should say that this is an well. So far, just so. By the way, what is this? What is this radical? It is a subobject, yeah. So it is a subobject. So it is in our case. The category of left A modules. So this means that we consider radical as a left ideal, yeah. So in our the following left ideals in A are the same. Okay, so the first one. The Jacobson radical. So this is intersection of all maximal left ideals. So section of maximal. So this is by definition, yeah, maximal left ideals. This is by definition. Next. Intersection of maximal right ideals. And finally, not finally, the annihilator. Of all the common annihilator of all simple A modules. And finally, the following set. So the set of all elements of the ring A, such that if we consider left ideal generated by X and shifted by 1, and then the resulting subset will consist of only of invertible elements. This is so. This is from this side. Actually, this is the same as well. You can imagine that since there is some symmetry here, So we define this as intersection of left ideals, but it turns out that the intersection of maximal right ideal, so there should be some symmetry, yeah, and it is in fact the case. So we can write that this is the same as the right ideal shifted. Sorry, so this was right ideal, so this is left ideal shifted by 1. It is also in the invertibles. And of course, if we have this symmetry, we can say that this is the same as those elements that such that the two-sided ideal generated by x shifted by 1 also consists of invertible elements. Yeah. So okay. So the question is, what is evident here? Which is what is evident? What maybe not? Well, simple maybe left, yeah. So here, simple, yeah, it's not clear. Simple left A models, yeah. Well, of course, you can imagine that if there is such a symmetry, then instead of left, you can write right models, yeah. So, well, I will not do this, but you can imagine that this is true. Yeah, so maybe it's I don't know. What do you prefer? Maybe it's easier to link these two. Yeah. What is the relation between maximal left ideals and simple left modules? How do you think of a simple left module? How could you get this? Yes, that's right. Yeah. So any simple, you see that if m is a simple A module, say left A module, then for any m which is for any non-zero m, there is a map from A to m given by so HA is sent to AM, yeah? It is simple, so this is its surjection, and its kernel is a maximal ideal, is a maximal left ideal. And conversely, if M is a maximal left ideal, then the quotient is simple. Okay. All right. So yeah, and of course this is M is the annihilator. Is it correct? Yeah. what is M? M is is that correct? Not. I'm not sure. So what is the relation between annihilators and so annihilator of, so it is annihilator of left module is a left module itself, yeah? Because when you yes, left ideal, yeah, it's a left ideal. Okay, so what is the annihilator of this module? M, why?
Because M is maximal and the non-annihilator is ideal.
No.
M annihilates.
Wait, you see that elements, what we have here an element M, but all other elements are of type AM. So we know that M is annihilator. So yeah, so so annihilator of M, small m, contains M. Yeah, that's we know. But why do we know?
But M is maximal. So annihilator.
Okay.
This is all.
Yes, yes, of course. Well, okay, it is, yes, it is equality. It is an equality, of course, yeah. But the question is why we are interested in the annihilator of M. So it is the annihilator of M is a priori smaller. Because you see that we have to, it is the intersection of all annihilators of AM, where A runs over the whole ring. Yeah. So why do you claim that this is an equality or not? Actually, I don't think that this is because yeah, so it is quite normal to have zero annihilator here. No? Or maybe not. Yeah, so so what would you say? Well, so I wouldn't, you see that we don't, but anyway, we don't need this, yeah? We need intersection of maximal left ideals, yeah? So, and these are maximal, well, at least if we may assume that AM is not 0, yeah? Otherwise it will be just this is an extra, well, we don't need this, yeah? Because this is the whole ring, and yeah, so we can, but these are maximal left ideals. And that's exactly what we want here. So we want maximal left ideals, and we get them. And vice versa, yeah, so we don't need, so you see that this may be 0, and it's not a problem, because in the section of maximal left ideal can be 0 as well, yeah, so no problem at all. You see that, so this way we get, yeah, so it's vice versa, we get from maximal left ideals we get simple modules, and from simple modules we get intersections of maximal left ideals. Yeah, and we don't need this. Yeah. All right, so this is inequality. And what about the rest? Well, so, ничего, нет?
Можно сказать, что значение первого и второе, потому что если мы добавим единицу максимальную,
Well, let's see. So we want so the claim is that if X annihilates all simple left A modules, then of course this one annihilates all X modules, yeah, simple X modules, and then this acts identically, yeah. Yes, it acts identically. Yeah, and if it acts identically on any on any simple module, then this means that this element does not belong to any maximal left ideal. Yeah. So if an element does not belong to any maximal left ideal, then it is invertible. Yeah. So because any non-invertible element, so any non-invertible element of A belongs to a maximal left ideal. Left or right ideal. Yeah? Is that correct? Because why?
You can just generate ideal on the server and use Zorn to say.
Yeah, so you consider the maximal ideal containing this element, yeah? Consider the maximal ideal, yeah, okay. And why is it maximal?
No, I say that we can generate ideal on this element. It will not be all green because it's not invertible.
Yeah.
So, and I say that we can partially order our ideals on inclusions, considering that there exists
The maximal.
maximum for some.
Yes, yes.
We can use Zorn to say
Yeah,
that
yeah.
maximum ideal exists.
Yes.
And
Yeah, but
we can можем взять факт. We have in commutative algebra correspondence with ideals that contains certain ideal.
yeah, but you see that when you pass to the quotient, then you get out of the category of rings. That's the problem in non-commutative case. So you just do not pass to the quotient and keep running. Either you pass to the modules, or so consider maximal submodule, or you stay in the rings, but then consider maximal ideals, left ideals containing this element. Yeah, and then the question is why. So you get the maximal. So suppose that you have an ideal which is maximal containing your element x. It is maximal in A. But why is it maximal? Well, I mean, it's stupid. If it's not maximal, you just extend it, yeah? So it is maximal as among all ideals, yeah? Among all proper, yeah? So it's not a problem. Okay, so the conclusion is that чего? Как бы, ну, просто максимальный среди содержащих данные элементы, он просто максимальный. Правильно? Ну, рассматриваем. Ну, yeah, the same argument. So you consider that you consider only those ideals that contain this element. And that's it. Yeah? And that is maximal in as just as an ideal. Now, so it contains now if an element annihilates all yeah, if it annihilates all simple all simple modules, then this element is identical on all simple modules, then it is not a maximal ideal in any maximal ideal, so it is invertible. And conversely, if this, so we have to prove that such elements annihilate all maximal ideal, all simple modules. Yeah, any simple modules is of this type. Yeah, it's a quotient of it's a quotient of some yeah, so it's quotient of some maximal ideal, and you see that such an element. So if yeah, so such an element is invertible. Such an element is invertible, and so why should it and we want to say that it is identical on any quotient like this. That's and why. Yeah, so it is yeah, so this this means that 1 plus xa does not meet, yeah, so it's it does not meet m, yeah, so what does this mean? So it does not, yeah, so it does not, yeah, it is, yes, this means, this condition means that it is in the complement, yeah, so what is this? This is just the complement to the union of all, yeah, so what is a star? So any, maybe we should put here any non-invertible elements, yeah, so maybe we should rewrite this as following. So this is, what is a star? A star is the complement to the union of all maximal left ideals, yeah? Maximal left ideals. And also this is the complement to the maximal right ideals, yeah? Okay. Is that correct? All right, and now, so what is the complement of, so this means that it does not meet any Yeah, so this is the complement, yeah. So it does not meet any maximal ideal. Which means that so what? Or maybe everyone is stated and we'll leave it as a homework. Oh. Так что. No, you see, we just have to check that this condition implies that such x annihilates all simple models like that. Yeah. How do you? So, for instance, what happens if we multiply this by x? Of course, there are two options. We may consider this. We consider left or right ideals. Yeah. So it's. For instance, if we consider this as if this is a left ideal and we multiply on the left, then this will be the image will be the same. Yeah. If this is an invertible element, and but it will not be, yeah, so yeah, so if Yeah, so the point is that one, you see that you have there 1 plus you see that here you have 1 plus x, yeah, 1 plus x as the image because it is invertible, yeah. So it is not an m. Yeah, so when we, well, let's try to multiply by x. What happens if we multiply by x? You see that the image should be, for instance, maybe we should look at this line, yeah? So if the ideal is left, M is left ideal, and then what we get is also the image, yeah. So will be yeah. By the way, maybe we can yeah, so or maybe let's, yeah, okay, maybe we can start with this. Well, at least, well, maybe we can start with the simplest case, yeah, with this one, yeah. So this one is definitely symmetric, yeah, so we don't really care which left or right modules to choose. So what happens when we multiply by this? When we multiply by this, we get the options are, so this will be either the same module or 0, yeah. So if it is 0, then it's okay, but otherwise it is the same module. What does it mean that this is the same module? This means that this means that axa plus m is a, yeah. Okay. But is that good?